In this video, I would demonstrate some basic data screening processes. In other words, how to assess whether your data is complete, accurate, and meets the assumptions of normality that is necessary for many types of inferential data analysis. So why do we screen the data? Why do we go through this step? And it should be mentioned that this is a process that you should go through before you do any other data analysis, before you even start to analyze and interpret descriptive statistics, or before you do any inferential or even correlational statistics. You should screen your data to make sure that it meets certain criteria. And so we do this to make sure the data set has all the values expected. In other words, do we collect data on all the subjects that we had anticipated? Are the data points that we collected, are they feasible, reasonable values? In other words, do we end up with values that don't make any sense based upon what we're measuring? So if we're measuring score on an exam that can range between 0 and 100%, if we have scores of 110 or scores of minus 15, those aren't reasonable or feasible scores for the variable that we're measuring. And then lastly, is the data appropriate for inferential analysis? And one of the main assumptions for doing inferential analysis, like a t-test or an ANOVA, is that the data be normally distributed within a certain range of tolerances. We can have some level of skew, but we like it to be more or less normally distributed, and that is one of the assumptions. So the screening process is designed to make sure we met these three expectations, and this allows us to make sure the data we're dealing with is accurate, make sure that the data is appropriate, and it meets the assumptions for further analysis. So let's first talk about checking for completeness of a data set. And what this means is basically, are all data points entered? So if we had 30 subjects that we're collecting data on, do we have 30 data points? Or do we have data that is missing? And this becomes important because if we have missing data points, this could result in an incomplete data set, or a data set that does not represent the sample as we expect it to. So if you know how many people or how many subjects you are supposed to have collected data on, it's really just a matter of making sure all those data points are available. So in order to do that, we are going to use some Excel output. So as you can see here, I have data that is basically height in inches for a group of subjects. And I know that I had 29 subjects that were measured. Now, to make sure that I have all my data points that I'm expecting to have, I go to the descriptive statistics analysis that I performed, and then I go to the count row, and I see that I have 29 data points. And so that indicates to me that I have all the data points that I expected. Now, when you have this size of a data set, it can be fairly easy to be able to see if there are missing data points. You'll have an empty cell. But if we had hundreds or even thousands of data points, it's not very feasible to scan through each row to make sure it has a value or is empty. So we can go ahead and use the count function within the descriptive statistics output to make sure that's the case. So in this case, I see here I have 29 data points indicated by the count here, and that's the number that I expected to have. So I have a complete data set as far as I'm concerned. Now, what would I do if I had values that were missing? In this case, I have all my data sets, so I've met this criteria, but if I have pieces that are missing, well, first I want to make sure I can check the original data collection forms that I might have had to make sure that that individual's data point was not just not entered, and make sure that it is then entered. If I do not have original data sheets or do not have a data point for that individual, maybe they weren't there for the data collection, or maybe they didn't answer a question on a survey, I have a couple of different approaches that I can take to kind of replace that missing data point. One of the first is what's known as imputation, or where I can impute values. And this is where I will use basically a regression equation to predict what that value might be based upon other variables that I may have collected on that individual. What some people will do is use the mean of the rest of the data points and replace that missing data point with the mean of the remaining data points. That has some drawbacks because it basically implies that that person would be average or would be typical of the other people in the data set, and that could grossly misrepresent what their actual value may have been. So I don't typically recommend that idea. And if we have more than one, if we have several data points that are missing, and then I replace those missing data points with the mean of the rest of the data points, that's going to do a couple things. That's first of all going to change the mean of the rest of the data set, and it's also going to make my standard deviation be more narrow. There's going to be less variance in that group now because I've added a number of data points that represent the center of the distribution, and so that's going to narrow my standard deviation slightly. And so that could now misrepresent what really may have been taking place within that sample. So I don't recommend replacing missing data points with the mean. Imputation is a bit more complicated, but it's a much more accurate, much more appropriate way to do that. Now, another approach would be if the number of missing subjects is less than 5% of the total number of subjects. So let's say I was supposed to have 100 subjects and I have maybe 97 that I have data for. So I have 3 missing subjects out of 100, which is 3%. I can just trim those subjects. I can basically remove those subjects from my data set. My data set now moves from 100 to 97 subjects, and I can move on and do other analysis. When it's less than 5%, you can do that. You can trim those subjects and not have it have detrimental effects on further analysis. When the number of subjects becomes greater than 5% and we trim them, that could result in some changes to the data set in which it no longer represents the sample or the population that we intended it to. So when we have more than 5% missing, we're most likely going to have to try and use the imputation technique versus trimming them or removing them. And this especially becomes true if we're doing an intention to treat analysis. If we're doing intention to treat analysis, we can't just trim those subjects. We need to impute the value using one of the techniques that I've talked about. So that's how we check for completeness of the data set, and this is probably one of the easier screening processes that we have to go through. Now the next has to do with checking the accuracy of the data set, and this refers to whether or not of the data values that I've collected, are they all feasible or reasonable for whatever it is I'm measuring. So as I mentioned before, if I'm measuring score on an exam, and the possible score on the exam could be anywhere from 0 to 100%, I want to make sure that all the data points that I've collected fall within that normal, reasonable range. And so if I find data points that fall outside of that normal range, I can either make sure that that wasn't due to a data entry error or some other kind of mistake, recording mistake, and then figure out how to deal with those. So in order to see whether or not I have any data points that are outside of that feasible or reasonable range, I need to know what that is. I need to know what that feasible, reasonable range might be. So if I'm measuring something that maybe isn't quite so finite, like percent correct on an exam, maybe blood pressure or BMI, then I need to know what a reasonable range of measurement might be. So, for example, measuring blood pressure, I could have a fairly low blood pressure, but a blood pressure of 10 millimeters of mercury or 15 is really not a feasible measurement in most cases. So I need to know what that range is. In order to check this, we're going to go back to our Descriptive Statistics output box. And so here we are in the Descriptive Statistics output box, and we're basically going to look at the minimum and maximum score. So we want to make sure that the minimum or maximum score that we've collected does not fall outside of that reasonable expected range. So again, if we were measuring percent correct on an exam and my maximum score was 115, I know that's not reasonable because that's outside of my 100%. Or if the minimum score was a -10, then I know, again, that's outside of my reasonable range. So I can look at that minimum maximum score, compare it to what I know to be my reasonable acceptable range, and make sure I don't have any data points that fall outside of that. And that's usually going to become pretty obvious when we look at that. So what do I do if I find inaccurate data points? If I find that score of -10 or 115 out of 100, what do I do with that? Well, we treat that very much the same way we do with missing data points. First, we want to check the original data collection sheets or the original data record, make sure that it wasn't a data entry error, and make sure that those can be corrected. We may have to impute the value, in other words, predict what the value probably would or should have been. Or again, if we have less than 5% of total subjects, we can trim those inaccurate data points from further analysis without worrying about how that might affect further analysis. So that's how we then would check the accuracy of the data set. And as I mentioned before, inaccurate data points will usually stand out pretty clearly to us as being inappropriate, but it's still incumbent on us to check for that. Now, the last element of the data screening process is checking for data normality. As I mentioned before, one of the assumptions for inferential statistics, like a t-test or an ANOVA or regression, is that our outcome, our dependent variable, must be normally distributed. And so we want to make sure that this data set has a within reason, normal distribution. Now, how we determine this is we check the skewness score that is produced for us in the descriptive statistics analysis output. So let's take a look at that. So here again we are in our descriptive analysis output, and you'll notice about halfway down the table here you'll see a score for skewness. Now, this skewness score gives us a quantitative measure of how much skewness there might be. And this score could be a positive or a negative score. If we have a score of 0, that essentially means we have a perfectly normally distributed set of scores. If it's a negative number, that means there's a negative skew. It's a positive number, that means there's a positive skew. And we have several criteria that we can use to make that determination of whether or not we consider it to be normal or skewed. And again, that's a relative term, relative skewness or relative normality. And so what we typically use is called the rule of 1. So if we have a skewness score that is greater than positive 1 or smaller than negative 1, then we consider that to be skewed. Now, if the skewness score falls within that -1 and +1 range, in other words, it's closer to 0 than it is to 1 or -1, then we would consider that to be normal. So in this case, with our data here, we can see we have a negative skew, but it's a very small number. It's much less, or much more, I should say, than -1. It's closer to 0 than it is to 1. So we could consider this to be normally distributed. Now, if this skewness score was, let's say, -1.7, then that's beyond that -1 criterion, and we could conclude then that that data set would be skewed. In other words, it's not normally distributed. So the skewness score is a more quantitative, more objective way to determine skew than possibly looking at a histogram or just comparing the mean, median, and mode. Because remember, in a normal distribution, the mean, median, and mode should be about the same value. But sometimes they might be off by a little bit, but that doesn't necessarily mean we have a true skew distribution. There could just be a small amount of difference between those three scores. So the skewness score gives us a much more objective way to track normality. And so in this case, as I mentioned, with this data set, we could consider this a normal distribution. So as I mentioned, in this case, we look at our skewness score in our descriptive statistics output and compare it to a skewness criteria. In this case, we're using that rule of 1. So our data set we're looking at had a skewness score that fell within that range of -1 and +1, so we consider it to be normal. Now, what do we do if the skewness score that we've collected falls outside of that rule of 1? So let's say, as I mentioned earlier, we had a skewness score of -1.7. What do we do then? Well, one of the main reasons we have a skew is due to something called an outlier. And that's a score that is much higher or much lower, or maybe both, compared to the rest of the scores. So we call that kind of an extreme score, a score that is much different than the rest. And outliers are the main culprit for creating a skewness. Sometimes inaccurate scores can also create a skewness. So if we have a score that's, if we're again measuring percentage correct on an exam and somehow the data gets inputted as a score of 1,000, that's going to significantly skew our data set. Now that's an inaccurate score. It's not an actual true score. It's inaccurate. But we might have a situation where an outlier is measured that's much different than the rest of the scores, but it is someone's actual score. So again, if we're measuring blood pressure and someone has a blood pressure of 250, that's not an inaccurate measurement. It's just an extreme score that's very different. It's a score that was actually measured. So that's what differentiates an outlier from an inaccurate score. Is an outlier was actually measured, but it is much different than the rest of the scores that were collected. So again, that our first goal then is in determining if we have a skew is to look for inaccurate scores. If we don't have any, we then want to look for outliers. And so let's first talk about how we look for outliers and how we can determine if a score is an outlier, and then we can deal with it. So we use a technique called the outlier labeling technique. And this is a technique that helps us identify if a score might be considered an outlier. And if it is, then we can figure out how we're going to deal with it. So it's a three-step process. And the first step is to determine a set of boundaries that we can say that if a score falls below this level, then it's considered an outlier, because we can have outliers that are scores that are very low. And also determine what's the upper boundary, that if scores fall beyond that or above that, then those would also be considered outliers. And so in order to do that, we need three values in order to help us determine these boundaries. And that's the score associated with the first and the third quartile. And then from that, we can determine the interquartile range. So let's look at how we can get that from the Excel data. So here we are back at our Excel data. And what I've done is I've used the quartile function to find out the score associated with the third quartile, which, as you may remember, is the 75th percentile. And then the score associated with the first quartile, which is the 25th percentile. And from this data set that I'm working here, the score associated with the third quartile is a score of 71, and the score associated with the first quartile is a 67. Now the interquartile range is basically, I take the first quartile score and subtract it from the third quartile score. And the difference between those two scores is my interquartile range. In this case, a score of 4, or a range of 4. So I'm going to use that value to help me determine what the boundaries might be, and then in order to then determine my outliers. So let's go back and look at the formulas here. So this brings us back to our second step. So now that I know my interquartile range, I can determine the boundaries for any outliers that I might have. So for the upper boundary, what I do is I take that third quartile score, and to it I add the product of the interquartile range and a constant, in this case a value of 2.2. Now, other authors and other textbooks will indicate if a score is more than 2.5 or more than 2 standard deviations from the mean, then that could be considered an outlier, or maybe even 1.96, that's considered an outlier. We're going to use the value of 2.2 to make that determination. And the reason we do that is because that will help us find out these outlier scores without trimming large amounts or potentially eliminating large amounts of our score distribution. So in order to figure out that upper boundary, here's our third quartile range score of 71. And to that, we're going to add that product of the interquartile range of 4 and that 2.2. And that gives us an upper boundary score of 79.8. So what that means in practical terms is that if a score in our data set is greater than 79.8, then we can consider that to be an outlier. Now the lower boundary, we take the first quartile, and from it we subtract that interquartile range times that constant of 2.2. So in this case, our first quartile score was 67, and to that